This is the Tutor Wizard. What we're going to do is mathematically model coronavirus 2 and see how that works with mathematical modeling. But before we do that, we need to power the engine. Let's do this. I'm going to have to use my piece of paper this time. SARS coronavirus 2, I believe, is the outbreak, which is severe acute respiratory syndrome of the type coronavirus 2. And so we're going to see how we try to mathematically model this and try to use that to help public health actually mitigate infectious disease like coronavirus. So here we go. What kind of people in our population do we have? And we're going to put them in categories, and then we're going to try and find the change of the populations of each of these categories, and then that's how we get differential equations, fancy things. Again, so I'll disclaimer before we start, I'm going to start using a bunch of bigger mathematical machinery. If you don't want to know the details, don't listen to the details, skip forward a little bit or ignore this completely, and you can just hear the story of how we model an infectious disease and try to use that to help public health mitigate it. With quarantine, or you've seen the quarantine scenario, that shuts down a lot of the connections. People can't mix anymore. I have a total population N, and then we need to see that there's going to be subpopulations of how the disease is spreading through the population. So I have S, which is going to be susceptibles. And then we're going to have, in this case, we're going to have infected individuals, but we're going to have this other category called E, which is exposed individuals, or you're infected but not infectious. So what this category means is you've got the disease, you're going to move from being susceptible to getting the disease, you're going to move into here, and you're going to have the disease, or the infection, don't say disease, you're going to have the infection. And then once you have the infection, it takes a latency period or an incubation period for that to go inside your body to actually create where you now are infectious. And then once that happens, you can eventually go to where you are removed from that category, is actually what they're calling it, or the recovered category, depending on your disease. So these boxes are different depending on your disease. Sometimes we just say essentially the latency period is essentially 0 for all intents and purposes. The common cold, once you've got it, you're infected and you're infectious. So we just have SIR models. Those are the classic ones. In the series that we do, we're going to go back to the basics, but right now I'm going to sort of explain the scenario for what the coronavirus model is going to look like. So in there, N is the total population, which is going to be the susceptible individuals plus the exposed individuals plus the infectious individuals plus the recovered. So before we start that, this is what we call susceptibles. And then these are going to be the category of what we call exposed. What that means is you are infected, but not infectious. Then what can happen once you're exposed and you do your latency period, you will become truly infectious. So this is the infectious individuals. And then you have the removed individuals. Removed usually means either you've been removed by death, or by death from the disease or infection, or you've been removed because you've been recovered and your immunity, like chicken pox and stuff like that, once you have it, you can't become susceptible again. You can get shingles later in life because the disease didn't actually, or the infection didn't actually go away, but you would be removed. Long story short, this is step one sort of when we have a certain specific type of disease or scenario in mathematics, we try to get compartments. In this case, what we want to look at is the total population of individuals that have an infectious disease spreading through them. Then what we do with that is we create boxes, SEIR. Those are for the types of people in the total population, and we're going to use this clever trick in some of our stages to analyze this later on. That N is the sum of those guys, and then we have differential equations for each one of those, so we can find the derivative of N, the total population, by looking at the derivative of these guys individually. I have to give a shout out to my PhD supervisor, Michael Yee Lee, and his supervisor, James Muldowney, who showed me how to do all of these types of things. But taking his classes and doing all the clever tricks that you see me doing here is basically I learned from these people. What does this say? Essentially what this says is the arrows are, we just cleverly draw them this way because we have some experience, but what's going to happen now is you can have new people come into the susceptible population and you can have people be removed from the susceptible population. So these are the arrows of what's going to happen. For susceptible people, usually this is what we call the I'll write them down in a second what all these parameters are, so let me fill in the board and then we'll tell you specifically what each parameter is also and what we're talking about when we talk about this. Usually this is like a birth rate, essentially. It can be different things if you have immigration problems and those types of things, but you have an influx of a constant, so this is not dependent on time. It just, we're assuming for simplicity that it's a constant influx of new susceptible population, usually a birth rate or something. There's being a new population being generated all the time. So that's how you can get into this new susceptible category, is you can be born into it and you got no choice. Life lesson. You can choose your friends but not your family. They're stuck to you like a disease, not an infection. I can get out of this category by dying. So we are going to have a delta, we're going to have a death rate, and that we're going to assume is proportional to the population. So we assume that you can be removed from the susceptible category by dying of natural causes or something else unrelated to the disease or infection that we're discussing. So that's the death rate. And technically speaking, at first they do the death rate of susceptibles and then the death rate of the exposed and the death rate of the infectious and the death rate of the removed. And we're assuming what that means is you're being removed from the population through directly proportional to the amount of individuals in the population. And then for another simplicity, especially you're not going to want to see, so you can do these models with it not like that, but it gets much more complicated and you have way more parameters. But to reduce the parameters in this model, we're going to assume that these are all equal to each other, and even though in certain cases you can add an extra term in there a little bit, but you would assume that this death rate is slight, depending on the disease. This death rate may be slightly higher than the other ones because this is the category that has the infection. But for simplicity, we're going to assume that all the categories have the same death rate, roughly speaking. This one might be slightly higher, so plus an alpha or something sometimes. What else can we do? Then we have to go into how do you move from one, this is the harder part, and which different models will do, but we're going to follow these, especially for me, Michael Lee and James Muldowney, and these types of people who have shown me how to do the different types of forms of incidents or interactions between people. In this category, we'll do one at a time and then we're essentially done and we have all our parameters. We have to get how do you go from here to here and what's the constant, and how do you go from here to here and here to here. For here, what we're going to do is we're going to call this bilinear incidence. I'll write these down after we draw this. I'll write down what all these alphas are in a second. I'll have to use my cheat sheet. Here, we're going to assume that we have bilinear incidence. So what that says is mass effect or mass interaction, mass effect interaction. We're going to assume that we have, it's like taking something and then stirring it in, mixing it like in chemistry, or we're assuming roughly that the population, everybody has roughly the same chance to interact with each other, and everybody's stirred in a pot, and that's not really what's going on, but we have to start somewhere, and we have to say that roughly speaking everybody's interacting with susceptibles and infected, and how do you get this? So this is called, classically, the one that seems to work and model the best is bilinear incidence. What that means is you're going to have a parameter beta, and then we're going to have, I'll explain. Right now I'm just showing how we set up the model. We can do more detailed talks when we go back in the series. I'll prepare and tell you in each step slowly, and even more simple models, how we come up with these kind of ideas of why would we use bilinear incidence and these types of things. What that's going to say is I have infected individuals and they're going to try and mess with susceptible people. So don't worry about the diagram right now. You have susceptible people walking around in the population and infected people walking around in the population. And this is why they're having the quarantine or self-isolation right now. So you stop doing that. So you can't have I's touch S's. So what they're saying is, roughly speaking, everybody's mixed in a pot homogeneously, and you can roughly have where if you come in this is the relative contact rate of an infected individual coming into contact with a susceptible individual. And what we're going to say is you can be, this infected individual has the probability of infecting this susceptible person at the rate beta roughly. We'll go through that in more detail. But for now, that's how we think that the susceptible move from this category by interacting with the infected individuals. In this category, what we have is we have a latency period, or we have an average time that you will be infected but not infectious. And so what we're going to do is I'm going to call it epsilon E. And what that says is you eventually move from being exposed to the infection to being truly infectious at a rate of epsilon proportional to the population. So this moves into here at the proportion directly proportional to the population. And the same thing here, we get a gamma classically of I. That means that you have an average infected period where you're infected for the common cold, you're infected for a week, and then you go into the removed category, or you recover from this. Overall, this is essentially our basic transport diagram, or what we are going to use to set up differential equations to actually model the change. From this thing now, we have a rough basic model of how we think in a total population broken into susceptible individuals, exposed individuals, infectious individuals, and removed individuals. We can now basically say that we want to know over time, how are these changing? And so if you don't know much about math and you haven't taken calculus or those types of things, when I talk about derivative or ds dt, that's the rate of change of the population of susceptible individuals over time. And we want to know how that's changing in this box. And we want this to stay big. Susceptibles are good in this scenario. Infectious, bad. Don't go around saying that to people. Just because you're infected doesn't mean you're bad. But we want this to be large and this to be small in the models, and we want to see how we can do that. And this is the next stage of what we're going to start doing. Next stage is we're from this transport diagram. Transport tells us how we're transporting the disease through the population. And from this, we're going to derive differential equations, which tells us how this population is changing over time, and this population, and this population, and this population. So we're going to get 4 equations, which are differential equations, and then we need to solve them and get clever tricks. That will be the next stage. We can see the transfer diagram that we've created for the populations, remembering that n is the sum of all of these populations. We can now explain, let me explain a little bit better what we meant by each of these and how we're getting these movement in and out of the boxes or out of each population. So delta is the constant death rate, and we're going to assume you can, in different models, and when you want to get more and more complicated, again, good advice to me was, if you're going to complicate the model and make everything worse by introducing 4 parameter values instead of just 1 delta, you should have a good reason as to why you want to complicate the system. If it doesn't seem to give you any more insight into the specific questions you're asking in the model, then you shouldn't complicate. So for all intents and purposes, especially just to explain how this works, having those guys just complicates a lot more, and so it's not necessary. So we assume that these are all the same death rates, even though this one, especially most likely, these ones would be higher, but we're going to, for simplicity at first, assume they're the same. Lambda, capital lambda, is going to be the constant influx of new susceptibles, often the birth rate of, in a lot of scenarios, that could be the birth rate, or people coming in. If you have a given population that's infected and then outside they're not, then that's how people can keep coming in. We just assume that also, for simplicity, is constant over time, that if there's a rough constant influx of new susceptible individuals. So that's how you can get in. Getting out is you die or you become infected. When you become infected, we're calling this the exposed, because now you've been exposed to this. And let's re-explain that. What we're saying is these two are essentially the same box, but they're slightly different sub-boxes inside there. If you're in either of these categories, you have the infection. So in either of these cases, you have the coronavirus. But here you have the coronavirus and you can't give it to anyone else yet. You're infected, but you're not infectious. There's a latency period, we call it, before that happens. Then you would move into here at directly proportional to how many people are exposed at the time. So that's how you move from being exposed into here. And then what we're saying is how you get from this box and why you move into here is because you can't move from susceptible directly into the infected, because you can't immediately infect people. So when this guy is moving around in space, actual space, and interacts with someone who's susceptible, and then that gets them, it will be somebody from this category who makes someone from this category infected with the infection. Our bilinear term is mass action. Incidence term, we're assuming that we're roughly mixed homogeneously, and then everybody has the equal chance of interacting with everybody, and that's the rate at which this guy would come in contact with this guy to make you susceptible or infected from being susceptible. And then you would immediately move into this category, because you would be have the infection, but you can't spread it yet. Then you would move from being infected to infectious, where you can now spread the disease, and then eventually you will move from being infected, in this case, to being removed, which means either you've recovered from the coronavirus or you've died or whatever else scenarios they have, but essentially that's the box of being removed. So epsilon is the latency transfer rate to infectious, and gamma is the recovery rate of infection. Basically what that means is 1 over epsilon is the average latency period for, so 1 over epsilon is the average period of time for which you would be infected, but you can't infect anybody. And then you will transfer into this category. 1 over gamma is the average infectious time, how long you would be on average infected with the coronavirus. Now what we're going to do is, step 2 is, once we have this transfer diagram, what we're going to do is derive the differential equations from this. In this case, we're going to have 4 differential equations. The differential equations, again, what we're trying to say essentially is we're going to take the rate of change over time of the susceptible population, the exposed population, the infectious population, and the removed population. Now that we have the differential equations from the transfer diagram, what we want to do is we want to essentially analyze positive solutions. We can't have negative, these are populations of individuals. We can't have negative 100 people in any of the categories. This won't make any sense. So what they're also doing is, when we're mathematically modeling, they're going to call it a feasible region for in the positive orthant, they call it. So in 4 dimensions, so in 2 dimensions you have 4 quadrants. In 3 dimensions you have 8 octants. In 4 dimensions you have 16 orthants. Which I can't picture anymore, but there's a bunch of them. So what we're looking for is a feasible region where we would have a solution or non-negative solutions to some of these. What we ideally actually want is which is what's going to happen when we analyze further at equilibrium, we would like this guy to be a positive number, the susceptible individuals, and we would like these to be zeros so that there's no disease. That's what we would want, and you'll see when we get this, that's what it's called, the disease-free equilibrium. When this guy's population is positive and the other ones are 0, that meant there was no outbreak, nobody ever got exposed, nobody ever got infected. Good, that's what we want. And then the other one is going to be the disease or the endemic equilibrium. When the disease comes through and the coronavirus goes through, it's going to stay in the population, and then when it reaches equilibrium and none of these change anymore, roughly, we want to know, is there a positive value for each of these? And that means that there's a positive value of susceptibles, infectious, and exposed, and everybody else. And then we're going to try and see how we can minimize those numbers. And then they call it the general reproduction number is going to be the tipping point for which that will happen. So stage 2 or stage 3 essentially is, once we have the transfer diagrams for basically modeling and discussing with all of the bigwig scientists and who I learned from essentially of how to set up those transfer diagrams of, we look at the disease specifically, we try to check which kind of scenario or model will best fit and what kind of categories of people we have. Once we have that, we derive differential equations. Now what we want to derive is, based on these differential equations, what's a feasible region for when we would have a positive solution, is what we're going to do. We want the feasible region now, and unfortunately I'm going to follow the classic notation. They're going to use the feasible region sigma. So sigma is not a sum anymore, it's not index, it's a set, it's a subset of R4, and what we're looking for is a feasible region or a region in the positive orthant of R4 that will give us meaningful solutions. What does that mean? We want the total derivative n of the total population to be increasing. So we're going to look at dn dt, and what we want essentially is for that to be positive. To do that, what we're cleverly going to do is, what was n, remember? dn dt is equal to d dt of n is s plus e plus I plus r. And then I can use linearity of derivative. Watch the other videos on linear operators or linear transformations. It is a linear transformation, so I can split the sum. So this is ds dt plus de dt plus di dt plus dr dt. And then a few minutes ago when I was saying, notice that he's a negative and he's a positive and he's a negative and he's a positive, everything's going to cancel because now we're going to add those. These are, now we have expressions for those. So we're going to put those in there. This is equal to ds dt is lambda minus beta Si minus delta S plus this one plus dE dt is plus beta Si minus epsilon E plus delta E. Oh, we're going to have to use the whole board. Plus this guy plus epsilon E minus delta I minus gamma I. And then plus the RDT, which is gamma I minus delta R. Now, let's watch. Cancel, 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 cancel. No, not you. Delta stays. That's the clever trick. If he'd canceled, I wouldn't have been able to see it. I'm pretty sure years ago when Michael made me do this, in the homework, one of those, I canceled the wrong one, and then you can't. I'm going to cleverly combine those to be N, and then it's like, where'd the I go? Where's... Yeah, don't do that. What do we have left? Clean it up. When we clean it up and we keep all of the things that hadn't canceled off, we get this. And that is, we're going to be clever again. I stole all these tricks from my supervisors, but now I get to show them. S plus E plus I plus R. And that, of course, says that we have that dN dt is equal to lambda minus delta n. And we want that to be positive. We can solve that and get a condition for n. Copy. Lambda minus delta n is greater than or equal to 0 if and only if lambda is greater than or equal to delta n. This says if and only if lambda minus delta is less than or equal to n. That gives us our feasible region. And remember, n is S plus E plus I plus R. Long story short, you're going to have to take Michael Lee's classes on mathematical modeling of infectious diseases, these summer courses or these types of things. But otherwise, what that gives us is sigma, which is points S, E, I, R in R4, such that S plus E plus I plus R is less than or equal to lambda over delta. Remember, in most of these cases, lambda is essentially the birth rate of the population and delta is the death rate. So this is the birth rate over the death rate. But this is the feasible region they're talking about. So we're going to try and look for disease-free and endemic equilibria when the disease spreads and when the disease doesn't spread inside this feasible region. When the derivatives are 0 and looking for, now what we're going to call them stars on everybody to find out when the derivatives are 0 and there is no change anymore, what kind of equilibria do we have? Let's label these first of all. 1, 2, 3, and 4. I can immediately see from this one that because it's 0, epsilon E equals delta plus gamma I, or I is equal to epsilon over delta plus gamma E. I depends on this. And from this one, I see that gamma I minus delta R equals 0. So that says R is gamma over delta. Don't skip steps. I'm skipping all the steps. So I moved it R over and then I divided by delta. And then how do I see? I was like, how do I relate that to E? I depends on E, so I can cleverly get rid of I now. I is epsilon over delta plus gamma E. Why have I made that move? Noticing from 3 and 4 that I and R depend on E, I can focus on E temporarily and find out and get 2 cases on whether E is 0. If E is 0, I and R are 0. Remember, if E is 0, then I and R are 0, and what does that tell us? The exposed people are 0, the population is 0. The infected population is 0, therefore, and the recovered the removed population is 0. That says there are no infections in the population anymore, 0, 0, 0. So then we can look at all 3 of these things being 0, dependent on whether he's 0 or not 0. We can look at the kinds of equilibria we're going to get from that scenario. I use equation 3 and 4 at equilibria state to find out that I and R depend on E. So we're going to do case 1. E is equal to 0. Remember, what E represents is the population of exposed individuals, and we're saying there's no exposed individuals. And immediately we can see that that says that I is equal to 0 and R is equal to 0. And what does that give us? Therefore, from equation 1, we see that 0 is equal to lambda. I is 0, so this term goes away, minus delta S. And technically we're saying, I almost forgot, but we put a star to say that we're at equilibrium state. Don't worry about the star if you don't like the star. Everyone wants to be a star anyways. Stars. Everyone's a star now. The star to know it's at equilibrium state. So now I'm going to solve this for S star, which is lambda over delta. It reaches the maximum at that. What does that give us? That gives us disease-free equilibrium of P0, we call it classically, or I'm going to use the notation of my supervisor, which will be, remember, we're looking for an S star, an E star, an I star, and an R star. And we just found out that S star in this case, when we assume that the E is 0, we get lambda over delta 0, 0, 0, which is in our positive feasible region. Remember, if you add these things, you're going to get this plus this plus this plus this, which is less than or equal to that. So it's in our feasible region. So this is called the disease-free equilibrium in that region. And that's the only equilibrium we get when E is 0 in case 1. In our last step, in step 5, we're going to analyze the general reproduction number and analyze when this case happens and when my next case happens based on the system's parameters. We'll get there, just hang on. Let's do case 2. Case 2, we're looking for equilibria now when E is not 0. So immediately from these two equations from 3 and 4, I still see that that does say immediately that I star now is not 0 and R star is definitely not 0. What we're going to now do is, because I know all three of these things are not 0, I'm assuming that the susceptible population is not 0 either, because that's where they're drawing. How these become non-zero populations is they're stealing from the susceptible people. Give me one more of your people. And so then that's how they're becoming non-positive. So they're all non-zero. And what we're going to do now is I'm going to use 2 and 3 cleverly and add them, because 0 plus 0 is 0, and then I can get a clever equation to isolate what S is. And then we're going to find all of these guys dependent on S. And then we'll get a disease or an endemic disease equilibrium from this scenario. Equations 2 and 3 are going to give me this beta Si minus epsilon E minus delta E plus this one, epsilon E minus delta I minus gamma I equals 0 plus 0, which is 0, because they both equal 0. Clever trick. Again, not mine, I stole it. Coffee helps everything. Do we get cancely? I think we do. This one and this one cancel right out the gate. And then we're going to get beta Si minus delta I minus gamma I minus delta E equals 0. Now what are we going to do? First of all, I'm pretty lazy. I'm going to factor the gamma out of the I out of that. That was minus delta plus gamma. Let's pretend I did that the first time. I did. So I factor that out. Oh, these are all stars. I don't want to write stars on all of these. You can see why I don't leave them on. But I know who I is. I is this guy, and that's how I'm going to get E in there again. So I is this epsilon over delta plus gamma E. Let's squeeze it in here. You guys get out of here. We don't need that in the video. One more step. This gives me beta Si minus epsilon plus delta E equals 0. What does that give me? That gives me a way of isolating. Oh, I forgot to do it. One more move. Which one did I forget to put out? I did it when I cleverly did it here. He's a E2, so I forgot him. All right. One at a time. I mean, move slow and do each operation one at a time. Beta S, I was epsilon over delta plus gamma E. Let's put the stars on now. And you're like, where'd the stars come from? I don't know. Where do stars come from? Hydrogen and gravity and time. That's where they come from, roughly speaking. Turns out you need electromagnetism early on so that they will condense and accumulate and accrete, but that was another story. Minus epsilon plus delta E star equals 0. That's what I've got. What are we going to do with this? This is the last clever trick. What have we assumed in our original thing? I can factor E out and he's not 0. And if I have a product which creates 0, then this is an integral domain, fancy, which means the other guy has to be, one of them has to be 0. And if he's not 0, it's the other guy. This is beta S star times epsilon over delta plus gamma minus epsilon plus delta, all times E star. And he's not 0, so this has to be 0. That's epsilon beta over delta plus gamma S star minus epsilon plus delta has to equal 0. We're closing in, we almost have S star, and then everybody else depends on those guys. What does that give me? Let's squeeze it in right here. This tells me that S star is equal to, let's move this guy over, epsilon plus delta. And then we're going to flip it. That's, try that again. S star is equal to, we're going to move this over, so we're going to get epsilon plus delta. And then when I flip this to divide it, I'm going to get gamma plus delta over beta epsilon. This is S star in this case. In the last stage that we're going to do, we're going to derive the general reproduction number, it's called. What we're doing with this and what you're actually going to see with public health are going to actually show you this. They're going to show you the general reproduction number is 3.2 or 2.6, or what are they saying by this? Essentially, the general reproduction number is the number of new cases any single individual, infected individual, is going to create and produce or infect susceptibles, assuming we have a susceptible population which is entirely disease-free. For every infected individual that we introduce to the population, if the R0 is 3.2, what they're saying by that is that every infected individual over some period of time is going to infect at least 3 more people. And so the general reproduction number is going to, what we're going to do is we're going to find this R0 to be a number which is based on all of our parameter values from our system. And then we can start controlling in our system with the parameter values what the R0 is, and then we can try and mitigate terms in here. And if we could make this one go away or this term get bigger, then it would say that this thing would increase and decrease, and then we can try and control this number. And this number essentially is going to be, you'll see, a tipping point for when we have disease-free scenarios or when we have a disease. So we're going to want to control R0 from the system. The R0 is going to be related to the parameter values in here. And then we can work at mitigating quarantine or inoculations and those types of things, and start trying to model through the system, which will again will be further videos in the series. But basically R0 we're going to derive from the system, which is usually depend on the parameter values. Then we can try and control those parameter values in the actual real world system, and therefore control this and see whether the disease breaks out or not. What are they doing with this? Basically, let's start with this. We want, at an equilibrium, we want the susceptible population to be larger than or equal to lambda over delta, which is again essentially the birth rate over the death rate. But I just erased it, so let me cheat. S star we did find was delta plus gamma, delta plus epsilon over beta epsilon. We did that in the last stage. We found the endemic equilibrium. If I want this condition to be true, I can now put that in there and now put the parameters in there, and that's what we're going to solve and call R0. Let's do it, and then I'll show you what I mean by that. This is true if and only if I know what S star is. This delta plus gamma delta plus epsilon over beta epsilon has to be greater than or equal to lambda over delta. This is if and only if. Let's divide. These are all positive, so it won't change the inequality. All of these things are non-negative or positive quantities. And that will give us delta plus gamma, delta plus epsilon. I'm going to multiply by delta, and then I'm going to divide by, I think the best way to do this is the other way. I'm going to divide by these guys onto this side. These are all positive quantities also. So what do I get? This one I'm going to get 1 is less than or equal to lambda beta epsilon over delta, delta plus gamma, delta plus epsilon. And this is what we're going to call R0, the general reproduction number. Why is that? Because now we see that this was the case where, first of all, if this happens, we can conclude that we only get disease-free. And now we found a condition for our R0 for when that will happen. So let me rephrase that now that we've found what R0 is. Actually, I can erase the whole board. Therefore, when the general reproduction number is less than or equal to 1, we can control and there is no disease outbreak. When R0, the general reproduction number, is larger than 1, we have an endemic equilibrium which will exist, which says that all of these populations are going to be positive, and then we can try to use further analysis of the models to try and mitigate and control the R0 so this will become less than 1. Currently, right now, in the report, which was December or February 2020 this year, early February 2020, they're guessing that in the original area where the outbreak occurred, that in the reservoir source, that it's about 2.4 R0, and I think R0 was person to person about 3.25 right now, currently, where it's outbreaking. So that says for every infected individual, there will be 3 new cases over a period of time in a susceptible population. What we're trying to do is, because it's currently this, we're now trying to use the fact that we have a model that set up everything and we have a bunch of parameter values, and these come from the terms. So if we can control in the system or mitigate one of these terms or get one of these, see if we could make this big, that means that the R0 can become really small. If we can increase these values and we can make the bottom really big, that will make the R0 really small. And that means that we can get the R0, which is currently above 1, to start reducing to go to less than 1, and then we will get a scenario where we have a disease-free equilibrium only. And this is the strategy of analyzing, mathematically modeling. Let's recap one more time, and then I'll draw the clever coronavirus currently, as in the modern papers that I just looked at a few days ago, what they're actually modeling the entire scenario for. It was basically 4 of these models, or 3 of these models plus the reservoir. To recap one more time, what we're going to do is, to model coronavirus or any disease, what we have to do is we have to say we have a population of individuals that are being affected by this infection. So we broke everybody into categories of susceptible, exposed, infectious, or removed categories. So we broke the population into 4 boxes. But then we put arrows on the boxes. We're creating a transport diagram which says how is the populations of each people moving from being susceptible to exposed, or exposed to infectious, and then removed or recovered. Then what we did was we derived differential equations from those transport diagrams. And then our differential equations involved a bunch of parameter values, and we set up this based on logically how we think the disease is actually moving, or how we want to model how the disease is going. Now we have differential equations. From the differential equations, we cleverly found a feasible region where this differential equation system might have equilibrial solutions. Then the next stage was we actually looked at, set all differential equations equal to 0, and we looked at when we would have equilibria. We had 2 cases, whether the exposed number of individuals was 0, and that says we just get the disease-free one because all of these guys would be 0, and then our susceptibles would be a positive population, which is essentially the birth rate over death rate. As long as your birth rate is larger than your death rate, your population will grow. This is population models. Also, we'll do a series on those ones. But Then the next stage, once we have our equilibria, what we want to do is to finally analyze. We're like, oh, that's all well and good. Here's a model. Here's how we think the disease is going. And then there you go. That's it. We wash our hands of it. What we're trying to do is now actually mitigate the disease and try to help public health and give them strategies for actually solving that. So what we do is we say we get a condition from the model that says we would like this certain thing to be positive. We want the S star to be greater than or equal to the lambda over delta. That happens when R naught is less than 0. So we call this guy R naught. He depends on all our parameter values. Now we can have a value which is essentially the number of new infected individuals over time from one infected individual. And if that's less than 0, that number from our model, we can say that there will be no disease outbreak or infectious outbreak. In this scenario, when R naught is larger than 1, we have that, and currently the coronavirus is 3.2. So what we want to do is try to control the parameter values in our model and try to come up with new scenarios for how to make it go from larger than 1 slowly to less than 1, and then the disease or the infection will stop. To recap, basically we're going to start a series on how to mathematically model spread of infectious diseases. We'll do different scenarios and different kinds of diseases. We'll get feedback from what people want to see possibly. But the first one, basically, because of the SARS coronavirus 2 outbreak, this is from, I've stripped off a bunch of stuff and simplified it somewhat, but from the papers that I've been reading about this, this is essentially how the original outbreak of the coronavirus has happened. So you can see that they have basically 3 models of what we just discussed: an SEIR model, SEIR model, SEIR model. This is the bat population, so the disease was actually in the bats originally. At some point, the infected bats got into the susceptible human, or the host population, they're calling it hosts, or the original infections. They don't know where this generates from, but then it seems like those hosts started, the main source of where this is coming from is the reservoir, or there was a seafood market somewhere in China where this has started to really break out. This information is coming from the Chinese Center for Disease Control, or in some of the papers that I was looking at. And then eventually from the market, this is how it's sustaining in our population, that the market is where we're transporting into the human population on a regular basis the coronavirus. And then in the human population, we have constantly feedback loops, it re-infecting the market and then infecting the population. In their papers, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 dimensional model. So we have 14 differential equations you can derive for the rate of change of this one, DSP people. And they've added this box. We didn't talk about this because I wanted a slightly simpler one, but this is asymptomatic carriers. These guys are all in the same box essentially. Now what that's saying is you're infected but you can't spread it, but once you can spread it, you can either spread it to, mostly in coronavirus it seems like children actually are asymptomatic carriers. You got it but you can't tell, so they're spreading it now but you can't tell, so they made an asymptomatic carrier box, and then or they made an infectious box. So from that, they're like 14 dimensions is awfully complicated, so they reduce it to saying we don't really need this scenario. What we're going to model is this, and then we have 1, 2, 3, 4, 5, 6-dimensional model, which is a lot better than 14 dimensions at the start. And this is what they're currently working on to deduce the fact that the general reproduction number of these models is about 3.26 right now. Science drop. Science to the rescue.